Welcome to this video on the topic of trigonometry. In this video we're going to do 3 examples to help us understand how we can decompose and solve worded problems. Now the first example we have from a point of 235 meters from the base of a cliff, the angle of elevation to the cliff top is 25 degrees. Find the height of the cliff. So we've got a worded problem here, and we're going to decompose it. Now the first thing we do when we decompose a problem is we have a look at what it's actually asking us to do. And in the very last sentence here it says find the height of the cliff. Now we go for another read through and we look for the key points. So it says from a point of 235 meters from the base of the cliff. So that's one key point. The angle of elevation to the cliff top is 25 degrees. So what we're dealing with here is we've got a cliff. So we'll draw a line representing a cliff, and we're 235 meters away, somewhere down here. Now we have an angle of elevation of 25 degrees to look to the top of the cliff. So what that means is the angle of elevation, or this guy in here, this is 25 degrees, so elevation meaning we're looking up. Now the location from the base of the cliff is 235 meters away. And what we're trying to find is the height of the cliff, so we'll denote it as x. X is the height of our cliff. So what we've got here is a mathematical diagram that's going to allow us to solve using our simple trigonometry. The only key feature that we still need to add to this is we have to put a right angle in here. So we're making the assumption that the cliff goes up 90 degrees from the ground height, which is fairly reasonable to assume. Okay, so now what we need to do is we need to look at the features we have on our particular diagram, label them accordingly, and then solve for the unknown x. So to do this, I'm going to look at the angle of interest, which is 25 degrees, and I'll call it theta. Then relative to theta we have the opposite side, which is represented by the value x, and we have the adjacent side, which is 235 meters. Now it's simply a case of going tan theta is equal to the opposite over the adjacent. Subbing in our values, we get tan 25 degrees, and that's going to be x over 235. Multiplying both sides by 235 to make x the subject of the equation, we get 235 tan 25, and thus we get to the point where we now need our calculators to solve. So I'm going to bring my calculator up and I'll put in 235 tan 25 and I'll hit solve. And thus we come to the conclusion that the cliff height, or the cliff face, is 109.58 meters tall. Thus concluding example 1. So the way in which we solved this was first we had a few sweeps over the question, and in each sweep we highlighted the valuable information that it's trying to communicate. After that we start constructing a diagram, so a simple diagram, so we can easily see the problem visually. So you first read the question, highlight the details, and then you try and create a meaningful diagram. Only after you create the diagram do you then start doing the mathematics. Alright, let's go down to example 2 now. We have a goalpost was hit by lightning and snapped in two. The top of the post is now resting 15 meters from its base at an angle of 25 degrees. Find the height of the goalpost before it snapped. Alright, so what I'm going to do is I'm going to go through it and I'm going to look for the goal of this question. So what is it asking us to find? And in the last sentence it says find the height of the goalpost before it snapped. Or we can say find the height goalpost before. So what was the original height? Now next sweep through I'm going to look for the useful information. So a goalpost was hit by lightning and snapped in two. So that's not very helpful. The top of the goalpost is now resting 15 meters from its base. So the top is resting 15 meters from its base, and it's at an angle of 25 degrees. So what we originally had was a goalpost. I'm assuming it's AFL or rugby. So a goalpost like this, and it got snapped. So it's now like this, and it's hanging downward like so. And what we're going to find is that the angle is 25 degrees. So this is 15 meters, and this guy is 25, and up here is where it snapped. Now, once again, we're going to assume that the goalpost points directly upwards, so 90 degrees, so we'll put a right angle in here. Now that we have completed our diagram, it's a case of simply labeling all the important features on it. So this 25 degrees, I'm going to call it theta, and the sides that we're interested in, we've got x over here, and we've got, no, we don't care about that one. We've got the adjacent over here, and what it's asking for is the original height, so markings of this red line here before it's snapped. So what we're going to do is we need to find the value for, let's say, x, which we'll call the partial height, so we call that opposite, and then the hypotenuse, which is also going to be, we'll call it y. So the final, or the original height, is going to be x plus y. So what that means is we have to solve for both the opposite and the hypotenuse. Now the first one we'll do is the opposite. So we're going to go tan theta equals the opposite over adjacent. We sub in our values, so we get tan 25 degrees. And that's going to be, opposite will be x, adjacent is 15. Rearranging to solve for x, we get 15, 25 degrees, and I'm going to leave it like that for now. Now the next one is we're solving for y. So y is going to be the adjacent and the hypotenuse. So we're going to go cosine theta is equal to the adjacent over the hypotenuse. Subbing in the values, we get cosine of 25 degrees, and that's going to be 15 over the unknown h. In our case, we called it y. Now, y is on the bottom, so what I'm going to do is I'm going to flip everything around. So y over 15 is going to be 1 over cosine of 25 degrees. And then rearranging by multiplying both sides by 15, we go 15 over cosine of 25 degrees. This is going to be our second part. Now the original height of the goalpost is x plus y, because it's going to be this section going up plus that section going down. So what we've got to do is we've got to add them together. So we're going to go original height is going to be x plus y. X is equal to 15 tan 25 plus cosine of 25, and that's underneath 15. And therefore, we bring up our calculators to solve this for us. We go 15 tan 25 plus 15 cosine of 25, and it comes out to be 23.5455. So what we have here are very tall goalposts. So once again, looking back at this particular question, the way in which we solve it is first we read the question and we first look at what it's actually asking of us. So find the height of the goalpost before it snapped. Then from there we read through a few more times, and each time we go through, or each read through, we highlight the critical information that's going to allow us to construct a neat diagram with all the information required to analyze. So what I'd done is I'd highlighted the length of the distance the goalpost is resting from its base, so this part to this part here, and then the angle of elevation. So if you stand at the goalpost say over here. If you look upwards, you can see the tip of the goalpost, so the angle that you look up at is shown over here. And from those two little pieces of information there, we can deduce the height of the original goalpost before it snaps. So once again, the challenge of this question is from the interpretation as opposed to the actual mathematics involved. The math itself is quite simple. Alright, final example is an aeroplane flying directly overhead. 2 minutes later, the airplane is at an angle of elevation of 27 degrees. Assuming that the airplane is traveling with constant speed, what will be its angle of elevation after another 2 minutes? So, once again, we read the question, we look what it's asking for, and it says, what will be the angle of elevation after another 2 minutes? So now I'm going to go through and have another sweep of the question. An observer notices an aeroplane flying directly overhead. 2 minutes later, it's at an angle of elevation of 27 degrees, assuming that the aeroplane is moving at a constant speed. Alright, so what's going on here is we have a person standing down here, and right above them there's an aeroplane, like so, and it's directly above. Now after that, the aeroplane flies for another 2 minutes, and it ends up, let's say, over here. So 2 minutes has passed, and the plane can be observed at an angle of elevation of 27 degrees, like so. Now the question is, what will be the angle of elevation after another 2 minutes has passed? So what will be the angle of elevation here? We call it phi. Now the way in which I interpret this question is the quantity that they're after is going to be the phi over here, but we have to do some careful maneuvering before we can get to that. The first part is we have to label these triangles in such a way that they're conducive to solving the problem. So what we want to do is have the angle of interest inside the triangle itself. So 27 degrees is outside. What we're going to do is move it inside by going 90 minus 27. That's going to yield 63 degrees. Now it's a case of we're going to find the height of the aeroplane over here, and from there, using the height of this triangle, we'll solve the interior angle of the green diagram, and then we'll solve for phi. So doing that, we're going to label our triangles. So this green one, we've got the opposite over here, we've got the theta, and we've got the adjacent by the looks of it. So we're going to get tan, do it in blue, tan theta is equal to opposite over adjacent. Then this is going to come out to be tan, and we'll have 63 degrees, and that will be 2 over x. Rearranging, we're going to get x is equal to 2 over tan 63 degrees, like so. And this is going to be the height that the plane is at, so the altitude. The next question is abstracting this diagram a little bit further. So we're going to have a green triangle, like so, with a right angle in here. And this side length, or the vertical height here, is going to be 2 tan 63 degrees. And what we're looking for is phi, which is outside over here. And we're going to know that the next part is up here is going to be 4. So when we're looking at the 2 meters up here, we've got another 2 minutes over here. So we're going to get a total of 4 minutes over here. So the first part is we're going to solve for this interior angle here, and we'll call it theta again. So we're going to have opposite and the adjacent, and we can write tan theta is equal to opposite over adjacent. That will come out to be tan of the unknown theta will be 4 over, and here's where it gets a little bit messy. We go 2 tan 63 degrees, like so. Alright, now we're going to take the inverse tan of all of this. So we go inverse tan And then we have tan 63 all the way down in the bottom. Then 2 sort of upstairs like that. And then on the very top we have 2 here, or we have 4. Alright, so this is our theta. Now, our phi, which is what we're interested in, is going to be, phi is going to be 90 take theta. So this will come out to be phi is equal to 90 take tan theta. And we're going to have tan 63 degrees all over 2, all over 4. And now it's time to bring up our calculator to solve this. So we're going to get shift tan, then inside the brackets we're going to get 4, then we're going to do more brackets and we're going to go 2, and all of that was 90 minus this guy. So that will equal 14.29 degrees. So the angle of elevation that the plane will be observed at will be 14.29 degrees when it's all the way over here. So this is probably one of the more difficult questions. If you were doing this and you didn't want to be as precise in the calculations, you could evaluate it step by step as you're going, whereas the course I've taken in this one is I've chosen not to use my calculator until the very final stage of the equation. The reason being is there's less error introduced into the calculations itself. So this has been our third and final example of how we can deconstruct worded problems and create diagrams to thus solve the problem at hand.